post this information on our XYZ site, but just so you have it now. On Monday, we won't meet as a class. Instead, I'll post a review video. You remember for our other 3 exams, the period before I just reviewed the topics, and so I'll do that on a video and post it. Should have it available in the morning on Monday. Okay? I'll also post some review problems. Probably sooner. On Wednesday, we have our exam. Here or via Zoom. And I want to know how you plan to take it. I'll find a way to get that information from you. Okay, and some of you maybe have talked to me about the need to take it maybe on Tuesday instead of Wednesday because of travel plans. And let me know. You want to take it on Wednesday, but can make some exceptions if need be. And then after that, there is just the final, which was remote for all people. I don't know when our final is. Does anyone know when it's actually scheduled?
It's on Friday.
Say it again.
It's on Friday.
December 5th, is it?
December 4th.
4th, thank you. So Friday, December 4th. Final exam, which is remote for everyone. And again, I'll let you know how that's going to work. We had to do it last spring, so we'll kind of do a similar thing. It's probably at 8 o'clock since our class is at 8 o'clock. And that's when you should plan to take it. If that's an issue, you can talk with me. And we might be able to let you take it with one of my other sections. And I don't know when their finals are, but just let me know. And see if we can accommodate you. Okay? So that's the plan. We go with it? All right. I'll be asking you for information. I may ask in an email. How many of you check your email regularly? How many don't? Okay. I was told years ago that email is like the younger generation. They don't use it anymore. They use text, and who knows what they've gone on from text. I don't know, Snapchat or things I've never heard of before. But watch for your email, an email from me, because I'll be asking you for information, and I'm going to need to know that information. And it's okay if my inbox gets overflowing with emails. I'll track through them and make sure there's a plan for every student. Welcome back, David. All right, are there any questions? I may have my assistant send out a Google poll and have you respond. I mean, if we can find a way to do it, that seems better than email. So watch for something from me in the days ahead. No questions. Questions on the homework? None. Good. It was a fairly lengthy assignment, wasn't it? 15 problems, maybe 14, something like that. But you figured them all out. All right. So here we are, the last day we can actually cover new material. We'll leave that on the board for a little bit. So on Wednesday, we talked about antiderivatives using the chain rule. A derivative fact, and we were able to flip it around and get information about antiderivatives. And I showed you how it works. It's a technique we call by substitution. And on Wednesday, because we didn't get to do it until later in the class, we didn't get very far. I did show you how the substitution works. And so I'm just going to do several examples. So find antiderivatives. One of the things that motivates us here is we discovered also on Wednesday, kind of Monday carried over to Wednesday, that to find the value of a definite integral, the very best way is if we can get an antiderivative, right? Then we just turn it into an arithmetic problem. So given that, then we want to be able to find as many antiderivatives as we can. So we did some earlier, just kind of taking the basic derivative facts, and now we're digging a little bit deeper. Like you want to find antiderivatives. At least one reason is so that we can find the value of definite integrals using the fundamental theorem. All right. So just several examples. X square root 1 plus 4x squared. So when we're doing u substitution, almost always there's a composition, and almost always, in fact always, except it can get a little tricky, we want to substitute for the inside function. So we're going to replace, just like I showed you on Wednesday, we're going to place 1 plus 4x squared with a new variable, u. So we're going to rewrite it. It's given to us in x. We're going to rewrite it in u. And we decide how we want u to look, and we want it to be the inside function. Well, then, if we're going to convert to u instead of x, I need to know how to convert the differential. Obviously, the function just becomes the square root of u. I mean, that's an obvious benefit we get. But I need to translate everything else, including the differential. Well, I showed you the way we compute these differentials. If u is a function of x, then u's differential is just the derivative of that function. Okay. Ax dx. And then I look and see, it's easy for me to convert the radical to u. Then I made the substitution, so that was easy. And now I have to look at everything else. Like, what's left over? Well, I got an x here, and I have a dx. Like, how do I convert that to my new variable? And if I look closely, see, there it is. There's an x dx. So all I need to do is cancel that 8 out. Let's divide both sides by 8. And I see that those guys go away. X dx, the leftovers, after I do the obvious substitution, x dx, I can write as 1/8 of a du. Okay, so we'll plug it in. That 1/8, it's a constant. We know we can pop it through. And then u is just, the square root is u to the 1/2 power. We know how to integrate that, raise the power, divide by, or since it's a fraction, invert and multiply. So the substitution turned an impossible, I mean, just by looking at it, an impossible antiderivative into a trivial one, the square root of u. See how it works? And finally, Once we've anti-differentiated, we need to rewrite it back in terms of the original variable. So that constant is 1/12, I believe, 2/24. Let's simplify it. And then I get u, which remember is 1 plus 4x squared to the 3/2 power. And at the very last step here, we'll add on our plus c. Okay? Questions? If you're thinking there's a simpler way to do it, you're thinking about it wrong. There's no product rule, don't think there is. Any questions? Part B. The integral cosine x over sine cubed. Does anybody have a suggestion for me? What should I let you be? Yeah. Cosine? Perfect. The inside part of a composition, right? Almost always. I mean, always to start with here. And then what's du, Robert? Yeah, cosine x dx. And we immediately get like 1 over u cubed. That's all my du, cosine x dx. Gone. And to set it up for the antiderivative, let's write it as a power function. Raise the power. Divide by the new power. Replace u with the function it is. I'm going to deal with that negative 2 exponent at the same time. Sine squared. Did it? Any questions? Can we check this answer to see if it's right? How would we do it?
Well, normally you would take its derivative.
Yeah, just take the derivative. So, yeah, absolutely. You can do it all the time. At some point, we'll develop enough confidence that maybe we won't feel the need to do it. But if you're forever unsure, just take a quick derivative. I think I told you on Wednesday, on the exam, there will be some antiderivatives for you to find, including some by substitution. And you want to make sure you get the chance to do all the problems on the exam. So, do your best. And then if you have time at the end, come back and check your answers. Take derivatives of your antiderivatives and see if you get the function. Now, and don't make a mistake when you're taking the derivative. I mean, it's pretty good advice to not make a mistake anywhere, but especially if you're checking an answer. Any questions? How about this one? Integral e to the 4x dx. What should I substitute for here? Is there a composition? Yeah, what's the inside function? 4x, that's what we'll substitute for. Then what's my differential? derivative of 4x is
4.
4. So we get e to the u, and then the only thing that's left is dx. Well, I can solve for it. Take that constant out. And we get just e to the u, whose antiderivative is e to the u. And then we'll plug in. Once we're done, replace u with what we set it out equal to at the beginning. Or, once you get a little bit comfortable with this, then maybe you'll do it like this. E to the 4x. Yeah. I'm gonna do it again, and maybe a little more efficiently. And if this confuses you, then don't do it this way. But I think for simple ones, and I think we'll say this is a simple one, we can make it work. I can look at that function, I can see the composition, exponential on the outside, 4x on the inside, and I ask myself, what's the derivative of 4x? And I tell myself the answer is, like, man, I really need a 4 here. Can you see the need for the 4? It's the derivative of the inside. It's the g prime on the formula we got from the chain rule on Wednesday. Well, I can't just multiply by 4. That's a different problem. What else do I have to do? I have to divide by 4. And I can move that 4 through the constant, we know. So I don't really need to spell out the details. I can just look and say, man, I got to have a 4 there. Okay, and I know how to pay the price. So I'm multiplying that problem by 4 over 4. That's 1. It's still the same antiderivative question. But now I just get e to the 4x. Now I have exactly the form from the chain rule that we used on Wednesday to come up with this idea substitution. And before we go on to part B, let's generalize. I think you'll agree with me, e to the ax, for any old constant a, what do you think the antiderivative is going to be? Yeah, 1 over a times e to the ax. You can see how that works. That's important enough to box out. Not that we couldn't redo it every time we see it, but I want to make sure we're comfortable with it. Notice it's the opposite of the derivative. And why not? It's an antiderivative. That is, for the derivative, we pop that a out in front, right? And now we pop out its reciprocal. Of course, because we're doing an antiderivative. All right, let's try this one. What are we up to? D. X squared square root of 4 plus 5x cubed dx. Someone tell me what to do. Let's try it. So one thing I can do on these is I can make a, hopefully an educated guess of what my u ought to be and then go for it. And if it doesn't help me, I can just go back and try something else, right? No harm, a few minutes maybe. So William says, let u be the inside function on a composition, which we have done every single time so far. Then what's my differential?
15x squared.
15x squared dx. Don't forget the dx. So obviously we get a square root of u. It's kind of like the first example we did. Once I do the obvious substitution of u, I'm left over with x squared dx. And I can see, there it is. I just need to divide by 15. And now we have an easy antiderivative. Raise the power, just like we did on the first example, multiplied by its inverse. Replace u with what it's equal to, 4 plus x, 5x cubed to the 3/2 power. We got it. If you're thinking like, why doesn't he do it this other easy way? You're thinking about it wrong. This is the only way. Okay? Remember, we don't have a lot of power. There's no product rule. There's no quotient rule. You've got to think about what do we know? And the only way we know is to do this. Now, we're super lucky that that power is 2. If it were almost anything else, this would be like difficult or impossible for us to do. You see why we're so lucky? Because when we took the derivative, bingo, a square showed up. And so we could tuck that square, that second power, into our differential. If it were the third power, couldn't do it. I mean, we could do it for 2 of the powers, but there'd be an x left over. And what in the world do we do with that x? There's nothing obvious to do. I mean, we could maybe solve this for x, but that doesn't look like a lot of fun. I would have to convert it to u eventually if I'm going to let my new variable help me find the antiderivative. Okay, so it's no coincidence that I had a third power and a second power outside just waiting there to get sucked up in the differential. All right, part E. The integral 4x over x squared plus 5. Does anybody see a composition there? It's a little tricky. For the moment, cover up the function 4x. Just pretend like it's not there. So what's left is 1 over x squared plus 5. That's a composition. It's the composition of the quadratic function with the reciprocal function. You see how that works? And the inside function, what is it? The reciprocal or the quadratic? It's the quadratic. So we're going to substitute for that. And then what's my differential?
2x dx.
2x dx. The derivative times x's differential. All right. So we get a u down below. There are a couple ways we can deal with the 4. Notice what we really need is a 2x. So let's take the 4 and split it into 2 pieces. A 2 here and a 2 there. We can move constants through the sign however we want to do it. I want to take half of that 4 and push it out of the way. So this 2 survives. And then what's left? Well, 2x dx, that's my du. So let's write it like that. Or you could write it like this. Those are exactly the same, whatever makes the most sense to you. Hopefully both of them do. So what next? Do we have a simple antiderivative now? We do. What is it, Elizabeth? Okay, the antiderivative of 1 over u. The antiderivative of 1 over u, Emma? Natural log of u. natural, it's the one power function that we don't use the power rule on. So I get twice ln absolute value of u. All right, there it is, the natural log. Hopefully you can see that. And now we substitute back, and I'm going to take advantage of something. Notice that our u can never, ever be negative. In fact, it's always bigger than or equal to 5. So the absolute value signs aren't needed. It's not wrong to write them, but I'm going to show that I know they're not needed. So there's our answer. You cannot because of the sum. There's no rule for distributing logs across sums. And there never will be a rule. That's the best we can write it. William, you could bump that 2 in as an exponent. If that's what you asked me, then you can do it. There's no real gain, but you can do it. But you can't break the log up over that sum. There's no way to do that. Logs don't break up over sums. Any questions? All right, F. So this problem appears to be out of place. Like we're looking at u substitutions where we substitute for part of a composition, and this is just a plain old simple function, tangent x, and you would be right. And but if you think about it, we don't know it's antiderivative, so maybe we can get it. Let's see. So the trick is to rewrite it. We absolutely should. I was doing it while you were telling me to do it. Good advice. Now there is a composition, just like on part E, where the reciprocal function is part of it. And so, just like we did on part E, let's substitute for the denominator. That's the inside part of a composition where the reciprocal function is the outside function. And immediately calculate du. As soon as we make a choice for u, you need to know what the differential is. And what is the derivative of cosine? Negative sine. So let's see what we get. I get u down below, and then, oh man, I'm only off by a minus sign. If I multiply by minus 1, then I can write sine x dx as minus, and let's take that minus 3. What over u to do? See how that works? What's the antiderivative? Yeah, natural log of the absolute value of u. Here our u can be negative, so we can't really improve on it. Cosine x plus c. The negative natural log of the absolute value of the cosine. That's the antiderivative of tangent. No wonder we've never seen it before. If you look in the book, no doubt you'll find the antiderivative of tangent written somewhere. And if you find it, they're not going to write it like this. And if you're remembering, if you learned it in high school in your calculus class, that's probably not what you remember. It's a perfectly good answer. Okay, but most people, most textbooks, they take that -1 multiple out in front and bump it inside as an exponent. Okay, they use a log property. And if you bump it inside, the exponent is -1, which means we're going to reciprocate that function, cosine. And what's the reciprocal of the cosine? Secant, yeah. So if you look in the book, if you ask, any internet site, they're going to say the antiderivative is the natural log of the absolute value of the secant. If you're remembering from your high school, that's probably what you remember. And I don't know why. I kind of like the first version. I can handle a minus sign, and I like cosine better than secant. I bet we all do. We understand it better. We can work with it better. We know the graph of it. Maybe we don't quite know the graph of secant right off the top of our heads. But both of those are correct answers. It doesn't matter to me if ever we need the antiderivative tangent, which one you choose you want to work with. They both are the same. So these are both good answers. All right. Let's try this one. A, B, C, D, E, F, G. (16x plus 4) all to the 12th power. Could have done this without U substitution, although we wouldn't like it very much. But we could actually raise 16x plus 4 to the 12th power using Pascal's triangle. But maybe there's a better way. Is that a composition? Yes, it is. The inside function is
16x plus 4.
And its derivative is?
16.
Yeah.
Dx 16.
So here's how I'd like for us to get to think about these problems. That is, we look at the inside and we say to ourselves, what's the derivative? It's 16. Well, let's get a 16 there. Now, I got to pay the price for that. So that I haven't changed the antiderivative. I've multiplied by 1, but I need the 16. I don't need the 1/16. Pass it through the sign. We know we can do that. And then we just get 1/16 raise the power by 1, divide by the new power. Let's see. And we have our answer. If we can't spell out the details, we're going to substitute for the inside. So here's u to the 12th, take the original integral. The only thing left over is a dx, so we can solve for dx by dividing by 16, and those guys go away, and we just replace it with 1/16 du. We have u to the 12th, raise the power, divide by the new power, okay? So you can, hopefully it's simple enough, you can just see we need a 16 there and pay the price. If not, go ahead and make the substitution and carry it out. Any questions? H. The integral from 0 to 2 x squared plus 1 to the 4th. Remember at the very beginning, I reminded us of the fundamental theorem. It says to find the value of the definite integral, first, find an antiderivative if we can. Okay? And that's why we've been focusing. It's one reason why. There are lots of other reasons why we've been focusing on it. A way to get antiderivatives. So let's let u be x squared plus 1. I think you can see that's going to work. Immediately find the differential relationship. So du is 2x dx Let's rewrite it. So I get a u to the fourth. And then I have left over an x dx. Well, I can see right there it is. I just need to cancel that 2 out. So we can replace x dx with 1/2 of the du. Just like we've been doing. But for a definite integral, we can make an adjustment that saves us a step at the end. Okay, like this. Definite integral x values went from 0 to 2. Now, because we can get a nice antiderivative, we changed it to this variable u. Well, that changes the limits, but I can calculate new ones. For example, when x equals 0, I'm going to plug it in over here, and what value do I get for u? 1. Yeah, so for a new variable, x equals 0 is the same thing as u equals 1. And when x equals 2, what do we get? 5. So I can just change the limits, and now I'm done with x. I don't need to write it back like we've been doing. I could, and then use the original limits, but I think it's better, it's more efficient to just change the limits. And so we get 1/2, and then we're going to get 1/5 u to the 5th, and then we're going to go from 1 to 5. See it? And now we just have an arithmetic. Like always, once we found our antiderivative. 1/10, 5 to the 5th minus 1. If this is an exam question, that's a good way to leave it right there. 5 to the 5th minus 1. I think 5 to the 5th is 3,125, but it doesn't really matter. We'll just leave it sitting right there. 5 to the 5th minus 1 divided by 10. Any questions? Elizabeth, you have a question in your eyes. You're just thinking.
How do you get that?
Get what?
5 to the 5th.
I plug in 5, I have my antiderivative, u to the 5th. I just plugged in 5, and then plugged in 1 and subtracted. Matthew. Did I make a mistake? So the fundamental theorem says, find an antiderivative, plug in the top number, minus, plug in the small one, the bottom one, right? I think it's correct. Any other questions? All right. Let's look at a special case here. So I have basically 10 minutes left to show you new calculus. And so we want to use this 10 minutes wisely. Suppose we have a function, I have a fraction here, and I have a function in the bottom. And by some miracle, I have its derivative on top. Maybe the derivative is just sitting there, or maybe I juggled constants like we've been doing. Okay, maybe I can make it be there. It's what we, yeah, it's what we did over here. I really wanted 2x to show up, and so I made it because all I was lacking was a constant. Then this guy, if we can get a function on the bottom, its derivative on top, then the antiderivative is the natural log of the absolute value of the bottom. Let's see. that's worthy of a box. And to justify it, if you're not sure, we're going to substitute. We've done this at least twice. In the examples, that is the outside function of a composition was the reciprocal, just like this one. So we substitute for the bottom, and then du is just f prime. And you can see we get 1 over u du, which we just saw right there. Okay. If you look back at the tangent, we could have used that. Right, the tangent of sine over cosine. Then I say, what's the derivative of the bottom? Well, the bottom is cosine minus sine. And so, man, I got the sine there. I'm missing the minus sign, but I can get any constant I want. So I'm going to throw a minus sign inside. I'll cancel it out outside, and then we get minus the log, just like we did it. All right. So a little more general result, which come in handy. Whenever I put a box around it, that means pay special attention. It might be like the thing we're going to use later on. I'm pretty sure we're never going to run into this guy again. This is just practice. If you played sports, this one is kind of like calisthenics. You do it to get warmed up, but it's not like you use it in the game. This one we'll use in the game, as well as the antiderivative of the tangent. All right. One more topic I would like to address. And I have about 7 minutes to do it. Remember, S of t is a position function for a moving object. And its velocity is v of t, which is what? It's the derivative. We know that. We learned that. That's nothing new. Let's bring it into something we're learning now. If I integrate the velocity function, for me to be, what do I get? Does anybody know an antiderivative of the velocity function? Scott?
It would be S of t.
Yeah, it's the position. I get S of b minus S of a. I get, so the integral is equal to where the thing was when at time a minus where it is at time b, advanced time, minus where, in other words, it tells me the change in position. Okay, there's a fancy word for that. It's called the displacement. It's how much the position changed over the interval. And it gets even better if velocity is positive, at least non-negative, everywhere in our interval. Then the object's always moving. And so the displacement's going to be just the total distance traveled. Okay? So the integral from a v of t dt is the total distance. So we're used to thinking of integrals as being areas, but if we have a position function, we know an antiderivative and we know what it tells us. It tells us position. And so we get another way to think about it. Or another way to think about this is that the area under the velocity curve is the distance. Right? Find that area because we know the integral also tells us area. That's going to be the distance traveled. Okay, so if velocity can maybe be positive and negative, then what we get from the integral is the displacement. If this is a positive number, it means it went further in the positive direction than it did in the negative over the time interval A to B. If it's a positive answer, then it went more in the positive direction. But if we know that velocity is never ever negative, then the integral tells us the total distance that the object traveled. Absolutely, I was just going to say it, William. Good question. Okay, so getting the most out of our last few minutes here. I'll assign a few problems. What you think about this? If you took the AP Calculus exam or even an AP Calculus class, you've seen these kind of problems because they love it. Every exam has one or two of these on it. If a population, it could be anything, biological, chemical, whatever, people is, let's call it P of T. Comma P of 2 has rate of change given by, we'll just call it P prime of T because we know the derivative tells us rate of change. Then the integral of that rate of change function from A to B is P of B because big P is an antiderivative, obviously. And same thing here. Like, this is the change in population. The integral tells me how it's changed if I know the rate of change. I'll do an example, but we're about out of time. I want to say one more thing. Currently, we all know that we're facing a pandemic. That's why I have to talk to you through Shield and you all protect yourselves from me so we can work together and hopefully keep everybody safe. Now, there are a lot of people whose jobs it is to project, like, how is this pandemic going to grow? And based on certain assumptions. So they make a conjecture, and you can do it from data. At what rate is it changing? And if they can come up with a function, then all they have to do is integrate it, and then they can say, in the future, this is how many people, when you read an article, it says, this many people are likely to be infected. It's because someone evaluated this integral. They made some assumptions about the rate of growth based on data. They don't guess, they just look at the trend, they make a conjecture, and then you can project that into the future. And it helps you set policy, like how do we deal with it? So we have classes that teach this. Differential equations is probably the best one. All engineers take it. Math majors are strongly encouraged to take it, where you dig into these kinds of problems. We'll get a start at it here. And I'll assign a few of them so you can kind of get the feel for it. Thank you for coming to class all semester. It's been unusual. I think as a university, we've done a good job. We had a little breakout lately, but it seems to be getting under control. 8 o'clock is early. While you haven't been the most talkative class, I'd say you've been attentive, and I appreciate that. And we're almost done. We have a couple of things for you to really focus on to get us over the end of the semester and hopefully into a good place for the spring semester. So thanks for coming and working hard. I apologize that I haven't gotten to know you so well. Combination of things, I guess. But let's finish strong and then have a wonderful break, and we'll see you in January after the final exam. All right?
Thank you very much.
Thank you, Scott. Yes,
Okay. I'll be in history class,
so ours is you will be all
okay, like you'll box them
well, yes.
Okay.
You can get the exam as soon as I post it.
Okay. So you'll post
And so I'll post it at 8 o'clock Pacific time, and then it will be available on Foxtel. I think to anybody in the world.
Yeah.
At that time.
I will be traveling on Wednesday, so is there a way that I can take the exam on Tuesday?
Absolutely. Okay, and I'll try to remember that. But again, like I said, I'll send out information and you can remind me.
Okay.
Okay.
Thank you so much.
Yeah, we'll make a plan for the Tuesdays.
All right, perfect. Thank you.
Thank you. Hi, we both thank you card because we weren't here for your in person. But we'll be down with it, yeah.
Oh, okay, well, thank you anyway.
Yeah, thank you. Thank you.
Should I open it now or should I wait?
You can open it.
Okay, thank you.
Bye.
Bye.